Have you ever stopped to think about the incredible, almost invisible technology that literally moves our modern world? I mean, from the moment you wake up to when you go to sleep, you are constantly surrounded by the work of electric motors. But how do they actually work? Let's find out.
All right, to get us started, here's a little question for you. Think about a bullet train just screaming down the tracks. Then think about the blender you used for your smoothie this morning. And now, picture a massive industrial robot assembling a car. I mean, they couldn't be more different, right? But what's the one piece of core technology that links them all?
You guessed it, the answer is the rotating electrical machine, or as you and I would call it, the electric motor. It's this powerful, super efficient engine behind pretty much countless devices we rely on every single day. And it converts electrical energy into mechanical motion with what feels like almost magical precision.
So, to really get our heads around how these amazing machines work, here's how we're going to break it down. First, we're going to look at the invisible force that makes it all possible. Then, we'll see how that force is put to work by the motor's core components. And finally, we'll dive into the clever balancing act that engineers have to perform to make these things work in the real world.
Okay, so part one, it all begins with some pretty fundamental physics. The big question is, how in the world do you turn electricity into actual rotation? Well, the answer is a force that basically shapes our entire universe, electromagnetism.
Now, the principle behind all of this is, believe it or not, beautifully simple. Whenever you run an electric current through a wire, that wire generates its very own magnetic field. That's it. That's the whole trick. A simple wire becomes an electromagnet. And this is the magic that connects electricity to magnetism, and it's the foundation for every single electric motor ever built.
So how do we turn that simple idea into really powerful motion? Well, engineers just amplify it. They feed electric current into these tightly wound coils of wire, and that creates really powerful electromagnets. Now, when you place these electromagnets near other magnets, doesn't matter if they're permanent ones or other electromagnets, their fields interact. They push and they pull on each other, and that physical force gets harnessed to create torque, which is really just a fancy word for a rotational force. And that's what spins the motor.
Okay, so that's the why, the physics of it all. Now for the what. Let's actually look inside the machine and see the parts that bring this incredible force to life. And it really just comes down to two essential systems.
You know, a good way to think about it is like a body. First, you've got the windings. Those are the coils of wire that carry the current. You can think of these as the muscles of the machine, the things that are actually generating the force. And then you've got the magnetic circuit. This is the engineered path, usually made of iron, and it's like the skeleton that guides and focuses those magnetic fields, making them as strong and efficient as possible.
Now, when it comes to arranging those muscular windings, engineers have two main flavors they can use. They can go with what are called salient pole designs. These have big, chunky coils wrapped around poles that actually stick out. They're great for generating a ton of torque at low speeds. Or they can use slot windings, where the coils are all neatly tucked into a smooth cylinder, which is much better for high-speed, really smooth operation. You see, this one design choice completely changes how a motor behaves.
So, what about that skeleton? Well, the magnetic circuit is just as important as the windings. It's usually made of laminated steel, and its whole job is to give that magnetic field a super easy path to follow, concentrating all that power right where it's needed to create maximum force. But there's one part of this circuit that isn't made of steel, and it's, you could argue, the most important part of the entire machine. Take a look at this number, 60 to 95%. What in the world could this possibly refer to inside a motor? Well, it represents the single biggest hurdle that magnetic field has to overcome.
Just as this quote from our source material explains, the huge majority of the magnetic effort is spent just trying to cross the air gap. And what's the air gap? It's that tiny, tiny physical space between the motor's rotating part, we call that the rotor, and its stationary outer casing, the stator.
So here's the crucial point. Get this. That tiny gap is everything. It's a massive obstacle for the magnetic field to cross. And because of that, it's also where most of the magnetic energy gets stored. If you make the gap smaller, it's easier for the field to cross. But if you make it bigger, you can store more energy. And this creates a really fascinating challenge for the engineers.
And that brings us perfectly to the final part of our story, the engineer's challenge. Because when it comes to designing a motor, there is no single perfect solution. It is all about making a series of very deliberate trade-offs. Yeah, engineers have to solve some really tricky problems. For one, those powerful magnetic fields can create these little stray whirlpools of current in the metal core. They're called eddy currents, and they just waste energy as heat.
So to stop them, engineers build the core from a stack of thin, insulated steel plates. Another problem, the magnetic fields aren't perfectly smooth. They can have harmonics, which are tiny imperfections that cause noise and vibration. So engineers use these clever winding techniques to cancel them out. And of course, all this work generates heat, which they manage with things like cooling fins and fans.
Let's circle back to that all-important air gap, because it's a perfect example of one of these trade-offs in action. You might just think, well, obviously make it as small as you possibly can. But, it's really not that simple.
Here's the engineer's dilemma. If you make the air gap smaller, you need less electricity to create the magnetic field, which is great for efficiency. But a tiny gap can also create other kinds of energy losses from small variations in that field. Okay, so you make the gap larger. Well, you solve that problem, but now you need way more electricity just to get the job done. So what do you choose? It depends entirely on what that motor is for.
And that, right there, is the art and the science of motor design. It's all about balancing the fundamental laws of physics with the practical realities of materials and manufacturing. And by carefully managing all these trade-offs, engineers create this astonishing variety of motors, each one optimized for its unique job, powering our world quietly and reliably.
Which of course leaves us with one final thought. As we push for more electric vehicles, more renewable energy, more automation, the demands we place on electric motors are only going to grow. The real question is, what new challenges, what new materials, and what new balancing acts will the next generation of engineers need to master to power our future?